So let's quickly go through the properties of the Bernoulli process. First of all, let S be the number of ones among n of these random variables xi. They are independent, they're all Bernoulli, so the number of ones among these n, the number of successes, if you will, in n trials, is a binomial with parameters n and p. So, in other words, the expectation of S is n times p. The variance of S, remember, they are the sum. S is the sum of n IID Bernoulli random variables, so the variance of S is the sum of the variances, but all the variances are equal to p times 1 minus p, so it's np 1 minus p. And finally, the probability that there are k successes in n trials is given by, quickly let's write down what we know very well, ps of k is n choose k, p to the k, right, 1 minus p to the n minus k. For k between 1 and, or 0 and n, because the number of successes has to be between 0 and n. Okay, how about the first arrival time? So we're doing this experiment. Let t be the time of the first success. So let t be the index of the trial on which we have the first success. Or, in other words, let t be the first index I such that xi is equal to 1. Well, t can be as small as 1. Okay, we can have x1 equal to 1. And t can be arbitrarily large. So this t is geometric, as we know very well from Bernoulli trials. Expectation of t is 1 over p. So the smaller the probabilities of success, the longer we expect to wait to get the first success. The variance, we computed this earlier, 1 minus p over p squared, and the geometric distribution, the geometric PMF is the probability that t takes the value small t is 1 minus p to the t minus 1 times p. Why? Because the event that the first success occurs on index t is the same as the event that the first t minus 1 trials result in failure, and the final trial, the tth trial, results in a success. Okay, the fresh start property. Remember, this is related to the memorylessness property of the exponential random variable, and the geometric random variable is the discrete analog of the exponential random variable, and it has this memorylessness property. So the Bernoulli process has the fresh start property. At every index, it starts again. For any given time I, the sequence of random variables xi plus 1, xi plus 2 is also a Bernoulli process, and this is independent of the past of the process. That is, there's a typo here, it's supposed to be x sub I. This is independent of x sub I minus 1, and all the way up to x1. Okay, so at any time when you stop the process and look at the future is independent of the present and the past, and it's as if the process has restarted. Okay, and finally, here's another way of memorylessness coming into the picture. Inter-arrival times. So the times between successes are geometric. In other words, also the times between failures are geometric as well by total symmetry. So let's I plus t be the time of the first success after time I. Okay. Then what is the distribution of t? So at time I, we look at the process. Suppose we had a success right at time I, and now we're wondering about the remaining amount of time until we have a success, and that is also geometric. Okay, with the expectation 1 over p variance 1 minus p over p squared, and the geometric distribution. So let's apply these properties on an example. Here's the example. Ayşe and Burak are playing a computer game. In each round of the game, Ayşe wins with probability p, and otherwise Burak wins. Okay? Find the PMF of the number of games won by Ayşe between any two games won by Burak. Okay? So the example is like this. Maybe we could denote the name games won by Burak with B, and then between them we have Ayşe and Burak and Ayşe and Burak, and then Ayşe, etc. So it'll go like this, a typical sequence. Well, let me not say typical. A sequence, a realization of the process, will be a sequence of B's and A's. Okay? Now, here we are asked to find the PMF of the number of winnings of Ayşe between any given two winnings of Burak. Okay? How do we do this? So let's write this as a probability. This is the probability that Ayşe wins k times, okay, between two winnings of Burak. Okay? In other words, if we fix the time right at the game where Burak won, okay, we're looking at the process from this point forward, and by the fresh start property, the game from this point forward is a Bernoulli process. So this probability can be written as the probability that A will win k times, okay, before B, given that B just won a game. Do you realize this? Do you understand this? Because we just use the memorylessness, or in other words, the fresh start property. Okay? So given that, so I'm focusing on a game won by Burak, and I will compute the probability that A will win k times before B does. Okay. Now, what is the probability of this for a given k? First of all, is k equals 0 possible? Yes, that would correspond to B winning twice in a row. Okay, so k can be 0 or 1 or 2 up to infinity. What is the probability that the number of winnings of A is k? Well, we want exactly k victories for Ayşe. That happens with probability p to the k victories in a row by Ayşe, followed by a victory by Burak. That happens with probability 1 minus p. Okay? So if you want to further make this interesting, perhaps, you could say Ayşe is Fenerbahçe, okay? And Burak is all the rest of the teams in the league, okay? So you're trying to compute the expected time. Maybe I said it the reverse. Let A be all the teams and B is Fenerbahçe. What is the expected duration, for example, between two championships gained by Fenerbahçe? What do you think? I think now this made this problem more, interesting suddenly. Okay, I can see that in your eyes. Okay, so let's rewrite. Let's think of it that way. So now, this is a win by Fenerbahçe, okay? Many years ago, okay? And this is the next one, okay? So now, what is the probability that k years will pass until the next win? We just computed that. Okay. All right. How about the expected number of years that pass with no cheer for the championship, with no cup? What is the expected number of years? So expected number of winnings by A between any two B's, right? That's what we're looking for. How do we compute this? Excuse me?
K'nın bu K'ya kadar olan toplamı bölü 2 çarpı K. Yani K çarpı K artı 1 bölü 2 çarpı K probability.
How about we use the fact that the expectation of the geometric random variable is 1 over P? So the number of games, starting with this one, up to and including the first win by Fenerbahçe. This is, let's call this T. T is geometric with parameter P, where P is the, 1 minus P, right? 1 minus P is the probability of B winning, right? So, I'm sorry, with P. P is the probability that A wins, right? So this duration, T, is geometric with parameter P. On the other hand, the duration that we're asking for is the number of losses we see before the first win, number of years that go by with no cup. What is that? That's T minus 1. Right? Because T also includes this one where we win. So this is the expected value of T minus 1, which is expectation of T minus 1, of course, which is what? 1 over P minus 1. Okay? So the better the team, or the more lucky the team, the higher the probability P. Is it? No. In this case, P is the probability of losing, right? So the smaller the P, the better. Let's understand this. Okay. Now, P is the probability of A winning in each game, and 1 minus P is the probability of B winning in each game. So T, the number of games until B wins for the first time, is geometric with 1 minus P, not P. Right? 1 minus P. Why? Because PT of T is, number of failures, T minus 1 failures, P to the T minus 1 in a row, multiplied by 1 minus P. Okay? So that is geometric with parameter 1 minus P. So we have here 1 over 1 minus p minus 1. Okay? So the better our team, the higher 1 minus p. As 1 minus p goes to 1, this expected time between two winnings goes to 0, which makes sense. So this goes to 0 as 1 minus p goes to 1. Okay? Now, I would also like to draw your attention to the fact that I took something as the soccer league, where there are many teams competing, and each could be modeled as having a probability of winning in each year. Okay. Now I took that, which contains many such teams, and I converted that to a process, Bernoulli process, with two. Essentially, it's like two teams, right? Why? How did we do that? Well, I merged all the other teams, except from one, as one process. Okay, so in every trial, it results in the success of our favorite team, for example, or not. So all the other teams are merged in the event that our team did not win. Okay, the winning of the other teams. Anyway, but I could have treated, for example, 3 teams who win independently, either 1 or 2 or 3 wins, and that would have been a multinomial process rather than a binomial. Okay, so let's switch to the next example. Yes, please.
Buradaki expectation of the condition değil mi?
No, this is the winnings by A between any two B's.
Ama biz bunun sonuna condition koymamız gerekmez mi hocam? Hani sondaki B'nin kesin olduğuna dair.
So the question statement has, in itself, the idea that the event I'm looking at contains a B at the beginning and a B at the end, and I'm looking at the number of A's in between.
Hocam şuradaki probability gibi yazamaz mıyız? Hani normalde A wins 3 times between 2 wins of B dedik. Onu da conditionlaştırdık hocam. Böyle bir şey olmak zorunda. Burada biz conditional değil, hani bir eksiğe yani biri aldığımız için bu şekilde yazamıyoruz.
Of course, you are using this. We could have done this by summing this, but I think we should take your question offline and move on to the next example. Okay. Now let y sub k be the total number of games played up to and including the kth game won by A. Find the mean, variance, and the PMF of yk. Okay. So this is a slightly different question. Now we are looking for not the number of games until the first win by Ayşe, but up to and including the kth winning. Okay, so it will be like B, B, A, and then B, 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 A, B, A. This is winning number 1, winning number 2, winning number 3, etc. And we are going up to the kth time that A wins. Now, how do we compute this? There are several ways of thinking about this. Here's the most straightforward way. Let's first write the event of interest. The event of interest is the following. Y sub k is equal to n means that it takes a total of n games for Ayşe to win k times. Okay? So this means that the first n minus 1 games are lost by Ayşe. Oh, wait. What am I saying? This is totally wrong. So this means that in the first n-1 games, A wins exactly k-1 times. A wins k-1 times. Right? If you look at the first n-1 games, A should win exactly k-1 times. And finally, the nth game should result in a success by A. Okay? And the nth game is also won by A. Okay? So we need these two things to happen. First, the first n-1 games are won by Ayşe, k times. So they're among the first n-1 games that are exactly k-1 victories by Ayşe, and then the last game is won by Ayşe. Well, using the fresh start property, the past events and future events are independent. So what happens on the nth game is independent of all the previous events. So this probability breaks down into the product of the first in the first n-1 games that are k-1 victories. The probability of that is n-1 choose k-1, p to the k-1, right? 1 minus p to the n-1 minus k-1, which is n minus k, multiplied by the probability that the nth game is 1, that is p. Any problem? So let's combine the p's. n-1 choose k-1, p to the k, 1 minus p to the n minus k. What is the range for n? What is the range for n? The kth victory for Ayşe can come as early as the kth game, right? But it's not guaranteed that it's going to happen in any finite amount of time, right? So, so n is bigger than or equal to k. Okay. So, how about the expectation of yk? This is, by the way, called the Pascal PMF. Let's compute the expectation of the Pascal PMF. Of course, one obvious way of computing the expectation of this PMF is to sum it, The PMF multiplied by n will be summed over all n. That's very cumbersome. Yes, please.
Senin karnın bir bulma ihtimali var mı? Sonuç olarak senin karnın oyunda kazanman gerektiğine göre n'in en tek kısmı yine k'ya eşit olmak zorunda değil mi?
N is the number of games up to, that include k successes by A.
Ama son oyunda biz kazanacağımıza göre o zaman k'nın da n'in top noktasına eşit olması gerekmiyor mu?
No, because k, for example, k could be, for example, 3, okay? So how long does it take for me to win 3 times? It could take me 100 games to win 3 times. Okay? So, okay. Still in your mind you can think of soccer, okay? But I'm using this language. Okay, so how about the expectation of y sub k? As I said, doing the rather than doing the summation, we'd like to approach it with a shortcut, and the shortcut is the following. Notice that this total number of games n can be broken up into k pieces. Why? Because first think of the number of games until A wins for the first time. And then the number of games until A wins for the second time. And then the number of games A wins for the third time. Right? Now let's call this x sub 1, x sub 2, x sub 3. Can you tell me the distribution of x sub 1? It's geometric with parameter p, where p is the probability of success, because x1 is the number of trials until success, up to and including the first success. By the fresh start property, x2 has exactly the same distribution, and so does x3, etc. So expectation of yk is nothing but the summation, or maybe the expectation of the summation of x sub i's. How many of them? K of them. There are k of them. I from 1 to k. Remember, k is a given. Okay? So this is, since the xi's have the same distribution, right, by the fresh start property, this is k times expectation of x1. Expectation of x1 is 1 over p, so this is k over p. Okay? So, maybe let me erase this part. Let's make some more room here. And finally, let's compute the variance of yk. The variance of yk is the variance of the sum of xi's, I from 1 to k. Again, by independence and identically distributedness of the xi's, this is k times the variance of x1. So it's k times p over 1 minus p squared, right? Oh, 1 minus p over p squared, sorry. Yes, please.
Şuradaki x var, x2 ondan tam olarak neyi ifade ediyor?
So this x1 is the number of games until A wins for the first time. x2 is the number of games starting from right after the game that A won for the first time. The next number of games until A wins again. You see? And by the fresh start property, they are all geometric with the same rate. All right, then the next topic is splitting and merging of Bernoulli processes. This will really prepare us for the Poisson process, which is going to be covered in the final lecture of this course. So this is really a simple result for Bernoulli processes. Show that when we split each arrival of a Bernoulli process independently with probability r, the resulting sub-processes are also Bernoulli processes with rate r times p and 1 minus r times p. And the question is, are the resulting processes independent? So what's going on is, for example, I'm standing at the door of this class, and for every student that comes to the door, I toss a coin with bias r. With probability r, I get heads and I let the student in. With probability 1 minus r, I send the student to the other room. Okay, so at the entrance, the arrival process for the students is assumed to be Bernoulli at rate p. What does that mean? Well, at every minute, a student comes with probability p, and no student comes with probability 1 minus p. Students come one by one. It's not possible to have two students coming in at the same time. So I have divided time. Remember, this is a discrete stochastic process. So I'm thinking of essentially discrete time So in every time interval, there's an arrival or no arrival. With probability p, there's going to be an arrival. With probability 1 minus p, there is no arrival, etc. So in this diagram, the dots mark the arrivals. Okay? And this is my xi process. It's a Bernoulli process of rate p. Okay? Now what I do is I split this into two processes with, probability r, each arrival coming to this process is sent into the next process. So I toss a coin, I decide whether or not to send this arrival to this process or not. I toss a coin at each of these. Okay? And if I did not send them to the red process, they will go to the green process. Okay? So those that did not go to the red process will end up going to the green process. Okay, did we get the number of dots right? So 1, 2, 3, 4, 5, 6, 7. Okay. Right. Now, let's call this process yi and this process z sub I. Okay? Tell me the probability that y sub I is equal to 1 for any I. For y sub I to be equal to 1, I must first have xi as 1, right? I must first have an arrival at the original process, and that arrival should be sent to the y process. Right? So the probability that I is equal to 1 is exactly equal to the probability that x sub I is equal to 1, and let's say the coin comes up heads, or I choose the red process. So this is by independence of the of the splitting with the original process. I can write this probability as the product p x sub I equals 1 times r. Okay? The probability x sub I is equal to 1 is given to be p, so this is p times r. Similarly, the probability that y sub I is equal to 0 is, well, 1 minus PR, right? Because if yi is not 1, it's going to be 0. So now, yi is either 1 or 0 with probability PR, 1 minus PR. And yi and yj are independent for any I and j. Why do we know that? We know that because the original xi process is a Bernoulli process, so xi and xj are independent, and the splitting is independent from time to time. Okay, so that means yi, yj are independent for I not equal to j. Hence, the yi process is a Bernoulli process at rate p times r, or rp. Okay? Any questions?
Hocam,
Yes, please.
şu P çarpı A dedik ya. orada x ayın 1 olması ve kırmızı proses seçmem bağımsız olarak.
Yes, so as I said, the splitting process is completely independent of xi's.
Ama mesela kırmızıysa x ayın 0 olma olasılığı yok yani.
So if a person comes in, I toss a coin independently from person to person. Yes, please.
Olduğu zaman o zaman the probability of xi eşittir 0 ve Bernoulli Process olmuyor mu? Hani o şekilde söyleyemiyor muyuz?
Can you repeat your question, please?
Yani bunun 1 eksi p çarpı r olması gerekmiyor. Toplumun probability'nin toplumun 1 olması gerekiyor ama hani 1 eksi p çarpı r yapması gerekmez mi?
So the probability that yi is equal to 1 is PR. The probability that yi is 0 is 1 minus PR.
Bernoulli'nin 1 olma olasılığı p. Diğerinin de hani green'e gelme olasılığı nedir? Şimdi ikisinin 2 olasılığı çarpı.
So hold your question. Let's do the following, and I think your question will be answered. So you tell me, what is the probability that z sub I is 1? What is the probability that we have an arrival in the green process? First, there has to be an arrival in the original process. That happens with probability p. And then that arrival has to be sent to the green, which happens with probability 1 minus r. Now, what is the, so basically let's complete this. The probability that zi is 0 is then 1 minus p times 1 minus r. Now, using these, what is the probability that x sub I is 1? X sub I is 1 if and only if either zi or yi is 1. But they are disjoint events. If zi is 1, we know that yi is 0, right? So, this is the probability that either zi is 1 or yi is 1. But they are disjoint events, so we can add their probabilities. This is probability that zi is equal to 1 plus the probability that y sub I is equal to 1. What is this? It's p times 1 minus r, and this is p times r. What does it give you? It gives you p. Okay, I think this answers your question now. Okay, so what have we learned? We have learned that the red process is a Bernoulli process of rates PR, and the green process is also a Bernoulli process of rates p times 1 minus r. Great. So we split a major Bernoulli process and obtain two baby Bernoulli processes. Now, are these baby Bernoulli processes independent of each other? Why? Okay. For different i's and j's, for example, take this I and take this j, clearly what goes on here is independent of what goes on over there. But at the same location, when you focus on one time unit, I think they are sort of dependent. Why? Because if you're standing here in the room, and you suddenly see someone entering, then you know that in that minute, there was no arrival to the other room. Okay? Because there's an arrival into this room if and only if, no, not if and only if there is no arrival to the other room. So they are dependent. Let's show that. So xi and yi processes are dependent. Example, just one example will be enough, right? the probability that x sub I is equal to 1 given yi is 1 is what? If yi is 1, xi has to be 0. So this is 0, which is different than the unconditional probability that xi is 1, which is p times r. Or sorry, I should have used zi and yi. I'm sorry. Let's replace the x's by z's and p 1 minus r. Okay, so the split processes are dependent. When we study the Poisson process, we'll show again that when we split a Poisson process independently, we'll get two Poisson processes. In that case, the resulting two Poisson processes will be independent, unlike this case. So our final example is the merging of two Bernoulli processes. So here's the example. Show that when we merge two independent Bernoulli processes of rates P1 and P2, the resulting process is Bernoulli with this rate, P1 plus P2 minus P1, P2. Okay, so in this case, we're doing the reverse. We take a Bernoulli process, which is, let's say, a red process. This is time. The red process has red arrivals. And the green process has green arrivals. And what we're doing is we record an arrival whenever either of the two processes has an arrival. Okay, so here red and green had arrivals in the same time interval, and we recorded that as one arrival in the merged process. And here only red had an arrival, only green had an arrival, only red, only green, no arrivals, only red, only green. Okay, the merged process is the following. Okay, let's call this x sub I, and let again the green process be zi, and the red process is y sub I. Zi and yi are merged to form the xi process. What does this mean? X sub I is 1 if either yi is 1 or zi is 1, or both, right? Or this or includes yi being equal to 1 alone, or zi being equal to 1 alone, or both of them being equal to 1 at the same time, and 0 otherwise. So let's compute the probability of xi being equal to 1. The probability that xi is 1 is the probability that yi is 1 or zi is 1. Are these disjoint events? They're not disjoint. Okay? So the probability of their union is the sum of their probabilities minus the probability of their intersection. Okay, so the probability of y1 being 1 is p1. This is p sub 2, and subtract p sub 1 times p sub 2. Okay, so we showed that when we merge two Bernoulli processes at rates p1 and p2, we obtain a Bernoulli process again, which is at the rate p1 plus p2 minus p1, p2. But it's very important here that we use the independence of the two processes to compute this product. I mean, compute this probability as this product. If they were dependent, this result would not hold in general, right? Trivial example, if the Y process was exactly the same as the Z process, when you merge them, you get the Y process back. You don't get any additional arrivals. You have a question?
Burada ikincide çıkardığımız şey, ikincide aldığımız şeyle aynı şey mi?
So, let's recap. In the first one, we have one P, a process at rate P, and every arrival is split independently into the Y process or the Z process. When you add the rates of the resulting processes, P times R and P times 1 minus R, you get P back. So when you merge them, you get the original process back. Here, we are merging a process at rate P1 and a process at rate P2. The difference is these may have arrivals at exactly the same time. So we need to discount this factor, which accounts for arrivals being possible at the same time. So basically, by definition, when you obtain two different Bernoulli processes by splitting one big Bernoulli process, the resulting Bernoulli processes will not overlap. And they are dependent for this very reason. But when you merge two independent Bernoulli processes, you get a rate that's lower than the sum of the rates of the original ones. Now, this is true for the Bernoulli case. It's not going to be the same. It's going to be easier for the Poisson case, which we'll address next time. Yes, please.
Rotasyonu alırken o için de bir yaptık, her için de bir yaptık. Y sağ y eşittir 1, z sağ y eşittir 1.
You're right. You're right, right. I shouldn't have used a comma here. Thank you. Or, this is really a typo, so that should not have been a comma. yi equals 1 or zi equals 1. Thanks for fixing this. Okay. So xi is 1 if yi is 1 or zi is 1. Okay, so this completes our discussion of the Bernoulli process, and the next topic is Poisson process.